this is the contents. I might speed it up a bit, just because I know we started late. But principally, it follows the standard technical approach as what's the problem, how do we get a methodology, some results. I'll start off with this video, which I think neatly captures the problem. And what we're doing in terms of putting the bow foil on the front of the ship is we are combining both of these effects to reduce the ship motions, because you have a lift component and also provide an additional thrust. So there's two key fundamentals that's going on here, and we're trying to capture that. This really started in the 80s, it really took off in terms of reducing the fuel consumption. So with the price of oil, it was looking at reducing and increasing efficiency. So a series of full-scale tests and the fundamentals of the physics and numerical models were developed during that time. And now we're at a stage where it's actually being implemented commercially. So, what's the scope of the project in terms of bow foils? So the first one is principally to evaluate the bow foils and develop tools so that we can understand the phenomenon in more detail and look where to focus our efforts in the future in terms of generating a feasible design which optimised for a particular ship, for a particular area, particular route. So this key part here is the first step on the way, and then with any technology you need to know the costs and feasibilities, and then finally actually the feasibility or the practicalities of putting it on the ship. Bearing in mind, as I said, with the wave foils, it needs to be retracted when we're not operating in optimal conditions. So it's quite a complicated setup, and this is really within the scope of the C-Tech, but we're primarily focusing on the first step. So where it is at the moment, I mentioned earlier with workboats and ferries, it's a sort of proven concept, but in terms of the goal of generating energy-saving devices for the shipping industry, it's not really it hasn't taken that next step to reducing emissions. And so our target is to look at larger ships, the 100-metre scale for short sea shipping, and look at how we can reduce emissions on those ships. To do that, our expertise is being applied to develop experimental methods for the design and evaluation of bow foils, but also numerical tools, so validating that can give us the ability to quickly assess other designs and potentially optimize. So this is our area of expertise. Today I'm going to take you through the experimental section to begin with, and how we've extrapolated that data to sort of a full-scale prediction. Ultimately, the entire program relies on testing with and without the foil. So you always have that benchmark without the foil that to compare against, and ultimately you use that to assess how well your bow foils perform. So the first step is really deterministic. So for this bit, deterministic, by that I mean either measured or calculated, calculating the response to the bow foil. And that's quite important because we need to understand the response before we even go on to the next step, which is the probabilistic. So in this area we are combining wave statistics, so it makes it a statistical prediction, and you have your design space suddenly becomes a lot larger. And putting in realistic routes, we can get an idea of what the full-scale prediction could be for different scales of ships, and we'll show you some examples of that. So the comparative assessment, what we wanted is a sort of understand the holistic response. So the effect of the foil on the motions reduces the added resistance, but you also have this added thrust component. Ultimately, it all comes in to reduce the power required of the propeller. And then we can take this increase in power and waves with and without foil and just get a number, efficiency again. And that's really what we wanted to get out of the project, but also this efficiency gain can be translated to emissions and fuel savings, which I'll show later. The ITTC has numerous methods for measuring the increase in power using model tests in irregular waves. You'll notice the first three on there, they're all done in regular waves, and then you take each component or ordinate in regular waves and you can perform spectral analysis and translate that into how it would respond in irregular waves. So it's more versatile from the point of view that it's deterministic and not statistical. If you run irregular waves, then you are having to run a lot of tests, and if you only have one C state, then it's very difficult to get an idea of how it will operate across a range. Which for any wave energy converter, which the Naval ultimately is, it's very frequency dependent, so it's quite important. Looking at those, ultimately measuring the torque on the propeller, we don't require open water propeller tests, which would be a further series of tests which we'd have to complete. And as you can see, they did a series of sensitivity tests for the different models or methods, and effectively the torque and revolution method came out very similar to the others. So for us, for simplicity, it can be running in a towed or free running, and because we wanted to do oblique seas, we decided to do a free running test. So we chose the torque and revolution model and designed our free running model, which is a generic cargo ship based on, I think it's over 500 ships, which one of our students put together, and from AIS data and various vessel databases around the world to get an idea of what a nominal bulk carrier would be like. And that's what we designed ultimately. It's 2 meters long. Normal ship scale is 100, so scale is 50. The bow foil, I'll talk about that actual size a bit more, but that's not a simple conclusion to come to in terms of how big you have your foil. And then we instrumented the system so that we could measure the ship motions, but also measure everything in the drivetrain. So we're just going back down to the sourcing, what the torque is, what the RPM is, and basically working out the delivered power and waves. The foil mechanism is spring-loaded, so it's constantly feathering to achieve the optimal angle of attack. You do get active or fixed systems. Fixed systems, because it's not feathering, you can get large angles of attack and potentially large dynamic stall, which is very difficult to scale. So we wanted a system which could feather, and active control is something we'd like to in the future that was beyond the scope of the task. So, and on this, we're also measuring the forces and the incident wave. So this is the concept. This is model instrumentation. Already said, got the bow foil with some springs at the top and the bottom. There's a strut, there's a pitching rod which runs through the vertical strut from the neutrally buoyant bow foil to a pitch encoder, so we can measure the foil pitch. And then we've got the wave probe at the bow there, you can see with the yellow light, and then also the force block with the wires with the blue cables coming off. That's a 3-axis force block, so we can measure X, Y, and Z. And the drivetrain, which we saw earlier in the video, we've got a torque meter, which is 0.1 Newton meters rated, so very sensitive because of the scale. Then we've got an RPM encoder and a motor. And the rudder, so this is it runs using autopilot, so there's a rudder servo with a potentiometer, and that's all recorded on the model. The fan is mounted on a system with a load cell so that we can calibrate it, and whenever we run it up we can actually see what load it's giving us, and because we're running at a constant speed, the skin friction correction is the same every time. So we calculate that in advance, and if you want to know more about that I can talk about it at the end. But ultimately we've got to fire up the fan to give us that offset in load. And on board we have the active call assist, so that's the motion capture system with the cameras. A Wi-Fi mesh system. We actually put one of the boosters on board the model, and that seemed to work quite well, and we get Wi-Fi across the ocean basin. We also have an accelerometer and a series of amplifiers for the loads, which all comes together on a small model, just about, it will just fit. So we fixed it, all our tests are done at the same Frown number, and then we testing frequencies which are similar to what we would see at full scale. So then when we extrapolate the results from regular to regular, they are actually representative of what might be observed by a ship at sea. The second aspect is the range of frequency. So we need to capture the operational envelope of the foil so that, again, this is a cliff edge problem, but in terms of the input parameters. So really, you have a situation where in very short waves there's very little motions, and you end up in a scenario where the foil isn't being driven through the water and going close to calm water because of the extra drag on the foil. When you get towards resonance, we've got large motions and the sort of resonant response to the bow foil, and then going to the other end of the spectrum, very long waves means you're effectively operating calm water again, which means you've just got drag in the system. So here, this isn't actually a result, it's just indicative of what we're trying to achieve. I drew that up at the beginning of the project, and we've got something similar to it, but ultimately, the bow foil has this operational envelope where the red bars you want to retract the foil because it's just not working anymore, it's just giving you drag. The conduct of the experiment, so we take a datum at the beginning where we measure everything, and you subtract any datum and forces from the actual measurements. You then have an acceleration in calm water, and then transient stage when you encounter the waves. That's where the model is effectively adjusting its RPM to get up to speed. And then your steady state stage, which is the bit we're interested in. Typically, in sea keeping tests, we're wanting to look at 10 wave encounters. The facilities that we've been testing at in the ocean basin here at Hensler, where we've done the majority of testing, we've been here for a week and a half. It's huge. The details on the slide, it's awesome. There's 120 paddles, you can create any sea state you want, and you can go wherever you want in the ocean basin. So highly effective test facility. Towing tank is up and running at Southampton, and we've managed to do quite a lot of initial tests there, testing our equipment, which are working. Some of the students have been using the model as well for their projects.
Run 28, recording in 3, 2, 1, now.
Running planner. Enabling drive. Switching to heading control.
Send away.
Switching to speed control.
It's a slight blip in the talking RPM. That's where voices is just coming onto the model, and so it's filtered because you get dropouts. So we have to, especially because we're differentiating the speed. Sorry, to get to the speed from the, so you do get these jumps. So we have to filter it before it's used in the controller. So when it's first initiated, you get this jump. So we send the waves, and the model makes its way up, and we need to make sure that this acceleration period happens at the right time so that we encounter the waves early enough to get the encounters we need, but then not too late that we end up with reflections coming back. So we need to, that was a fine balance, which we worked out after a while. Because in this run here, we're actually doing several headings. So this is the heave of the model now as it encounters the waves. And as I said earlier, you have this transient period where you'll increase the torque in RPM. I think this is with the foil, actually, so you don't get an increase. So it's not that helpful, because it's... and then when we get to enough encounters,
heading to 30 degrees.
put in a turn to 30 degrees, and then there's a transient stage there due to the turn as well. So we have to wait
speed around
until we're at the right speed, and we're also getting 10 encounters. So you can see here we're doing the turn, there's an increase.
60 degrees.
Once we're at, again, another 10 encounters, so stable 10. 6 screws. On the left hand side, this is the actual measured power. The red one is without the foil, and the blue one is with the foil, and you can see basically just cuts it out. So even though you do have still an increase from the calm water, which is the red dashed line without the foil, ultimately when you're running in waves out at sea, you can take out that entire resonant frequency with operating the foil. And when we do the calculation in terms of the reduction, you can see it a bit clearer. This is on the right is a comparison between the red and the blue lines, but this wavelength length ratio is slightly opposite. But here you can see that this is the cliff edge I was talking about in terms of the figure I had earlier, and so here we didn't quite capture it. But you have this envelope with a resonance at about 1.2. We have a 10% reduction in heave, so that's the top right there. You can see that it's mostly across towards the higher frequencies and lower frequencies, where the model is contouring the waves, you're not getting much effect. Pitch is a large reduction across all frequencies, and we also looked at the phase. You get, because the added lift force at the bow, you're getting a phase change as well in terms of motions. So the foil pitch, as I showed, is about zero in the and we're getting resonance as well. So when you go towards other frequency ranges, the pitch is less. Ultimately, that's because it's spring-loaded. That's ultimately related to the lift forces acting over the foil, and you can see that on the right-hand side with the lift force as well. So if you compare the blue, light blue on the left-hand side of the pitch with the turquoise, or not turquoise, sorry, the pink one, you get a similar trend, and that's principally down to this resonance effect when you are acting at a point where the foil has maximum motions through water, but also the waves are opposing the foil motions as well. So you're getting like a superposition of the wave effect and the ship motions. This is an example of the foil pitch at resonance. So we fit a sine wave to it and then take amplitudes and phases, etc., and frequency. In the graph behind, you can see that I've split these up into mean, upstroke and downstroke, because you do get a difference in your upstroke and downstroke thrust, and that's principally due to where the foil is in the wave as well. So you get this double peak effect, and we've seen that more so at the resonant frequency, and then it tails off, so the peak gets less when you go towards. This is the theory on this. It's usually the increase in torque and RPM is proportional to the square of the wave amplitude. So principally, we end up with a transfer function or an REO, response amplitude operator, for each regular wave frequency that we ran. And then we have an idealized spectra, which we then combine to get a pseudo spectra. And this is an example from our tests. So the top one is transfer functions measured in regular wave tests, so you can see the various frequencies across. We have to set limits, so at the limits you assume calm water, so without the foil that's basically no increase in delivered power or propeller RPM and torque, and then with the foil it's the additional drag. So we did the tests, we did calm water tests with the foil on board, measured the torque and RPM, so we can get an idea of what happens at the end of these, the tails as it were, of these spectrums. When we combine it with the wave spectrum, you get it's called a pseudo spectrum, and you take the area under the curve, that gives you the RMS value, and 2 times that is a significant value, which then you can transfer to any sea state. So now we have our idealized sea states anywhere in a particular region. We can apply that to our regular wave data. So, for example, in a full-scale significant height of 2 meters and a period of 7 seconds, we're getting a 12% reduction in delivered power. So, because we saw earlier our resonant response was up to 50% drop in delivered power, but when you start to take into consideration that the ship's operating in a range of frequencies, which some are suboptimal, you get this kind of drop in efficiency. So that's just going in head seas, long-crested. But in reality, you're going to be going at different angles to the waves, and you've got waves coming from different directions as well. So we did some turning circle stuff and just to get an idea of what the effect might be. It looked like a cost-squared relation. We've been in the tank since to assess this. But ultimately, in following waves, it doesn't add anything, it just adds drag. Then short-crested is also a sort of cost-squared assumption. As you move away from your predominant wave direction, you get a component coming from each heading, which is smaller and smaller as you get around to the beam seas. So we can put this all into the prediction as well. Now we have the ability to do that, we can apply it everywhere. And WaveWatch 3 is a hindcast data set where across the globe for series of, for long and lat, so quite fine resolution, you can get sea state information on significant height, the period, and the wave direction. So you can download this every hour for every 3 hours, and there's a hell of a lot of data. I take that all off the internet, put it into bins, and you get something like this, a scattergram. So this is basically how many waves occur for a particular sea state. And then you do the same for the wave direction, and you basically use these scattergrams to get a probability of occurrence. So now, in each box, we can do the analysis and relate that to the probability of occurrence, so we can get an idea of the overall efficiency. But to do this, we have to have an operational envelope. So this is like the cliff edges I talked about before. We applied it for frequencies, so that's either side with modal period, but also a minimum wave height. So if we go to 1 meters or below, it's effectively operating calm water. And then we have a practical limit at so that's a wave steepness where we have potentially structural problems, and the theory of linear extrapolation falls apart. So we set these practical limits and also the following seas assumption, and we apply this to ship routes and global. The ship route is divided into 60 waypoints, and at each waypoint you're grabbing the nearest wave data and doing the analysis. I did promise some videos, but you probably didn't think it would be this cheesy, so...